Welcome to Brain Vision.
In this question, we have the following setup. There is one big cube and there is one small cube. A force P is exerted on the big cube, which tends to move to the right because of the action of that force. Of course, this big cube also suffers the action of the weight force, and because of the weight force, the ground exerts a force N1 on this big cube. Now, for the small cube, there is another set of forces. The small cube is touching the big cube, and as the big cube is moving to the right, there appears a normal force in between the small cube and the big cube. And that normal force is exerted by the small cube on the big cube and by the big cube on the small cube. Also, the weight force tries to push the small cube towards the ground, while the frictional force tends to hold it in place. This is because the frictional force always opposes to movements or tendencies of movement, and the tendency we have here is that the small cube will slide down the big cube. And to avoid that from happening, there appears a frictional force. And then we have to discover what is the smallest magnitude of this force P, such that the small cube will not slide on the big cube. For that, let us choose a reference frame as this one. This is the y-axis, and this will be my x-axis. Now, to get some equations, we apply Newton's second law to both the small cube and the big cube. So, for the big cube, we get the following. On the x-axis, the net force that acts on the big cube is equal to the mass of the big cube times its acceleration. But that net force is composed by two forces, P and N2. So we get P minus N2 is equal to M1 times A1. Let us keep this equation. Now do the same for the y-axis. The net force on the y-axis that acts on the big cube is equal to the mass of the big cube times its acceleration in the y direction. Notice that it's not moving in the y direction, therefore its acceleration is equal to 0. Then the net force in the y direction is equal to 0, and the net force is composed by the normal N1 and the weight W1. Then N1 minus W1 is equal to 0, meaning that the normal force that acts on the big cube is equal to its weight. This was an obvious result, so this equation, I believe, is not really helping us to solve this problem. Now let us do the same thing for the small cube. For the small cube, on the x-axis we have the following. The net force in the x direction is equal to the mass of the small cube times its acceleration. But the net force that acts on the small cube on the x-axis is only one force, N2. Then N2 is equal to M2 times A2. And also, let us do it for the y-axis. Then, on the y-axis, the net force is equal to the mass of the cube number 2 times its vertical acceleration. We want it not to move, so its acceleration should be equal to 0. Then, the net force in the y-axis should be equal to 0, which means that the frictional force minus the weight number 2 should be equal to 0, and finally, the frictional force must be equal to the weight number 2. And now, how can we use those equations that we acquired to solve the problem? Let me erase the board and summarize these equations. We end up with these 4 equations. Now note the following. There is no relation between equation number 2 and the force P, so we are not using this equation at all. And there also seems to be no relation between the equation number 4 and the force P, but this is not the case. Because when P is the smallest possible, the force must be the biggest possible. Therefore, we must be working with the biggest possible frictional force, which in the static situation has a relation with the normal force. So, equation number 4 actually becomes mu static times normal number 2 is equal to the weight number 2. So it has a relation with force P because it has a relation with the normal N2. Then we will be using equations 1, 3, and 4 to solve this problem. Let me here write them. Okay, Now we begin by solving equation number 1 for P. This results in P is equals to M1 times A1 plus N2. Now we have to discover what is the value of A1 and N2. We can discover the value of N2 using equation 4. From equation 4, we get that N2 is equals to W2 divided by mu static. Then P is equals to M1 times A1 plus W2 divided by mu static. Now we have to discover what is the value of A1. And for that, we can use equation number 3. Equation number 3 tells us that N2 is equals to M2 times A2. Therefore, A2 is N2 divided by M2, and at the same time, N2, we already know, is W2 divided by mu static. So, we get this for the acceleration number 2. It happens that both blocks moves at the same time, therefore, A1 is equals to A2. Then, P is equals to M1 times W2 divided by mu static times M2 plus W2 divided by mu static. We can write it as W2 divided by mu static times M1 divided by M2 plus 1. And now, remember that the weight force is given by the mass times the acceleration of gravity, which is approximately 9.8 meters per second squared near the surface of the Earth. So, plugging in the values that the problem gives us, we get P is equals to M2, 25, times G, 9.8, divided by mu static, 0.71, times M1, 4, divided by M2, 25, plus 1. Then, P is approximately 400 newtons, or 4 times 10 to the second newtons.